Moriarty's goal is to maximize his viewing angle of the painting. If he stands too far away or too close to the wall, his viewing angle will be small. The viewing angle will be maximized at some optimum distance in between. That distance from the wall and the corresponding maximum viewing angle is what needs to be found. We are given some data that will be needed. Moriarty's height is 6 feet. The height of the painting is 12 feet. The painting is hanging on the wall and its bottom end is 8 feet above the ground, which means that the top of the painting is 8 plus 12 or 20 feet above the ground. Alright, let's set up the problem. It always helps to start in such cases by drawing a figure. We've got the famous Mona Lisa hanging on the wall. Let's assume that the bottom end of the painting is at a height A above the ground. Let's assume that the top end of the painting is at a height B above the ground. Assume that Professor Moriarty, with height h, is situated a distance of x units away from the wall. Now let's assume that the painting projects an angle theta to the observer. And so the objective here is to maximize theta. Because when we do that, we have the best possible view of the painting. The question is, how far should the observer be from the wall, the distance x, so that he has the best view or the maximum value of theta. To find theta, we define angles alpha and beta, which are angles made by the lines joining the top and the bottom of the painting with the horizontal. The angle theta, which we seek to optimize, note that it's merely the difference between the angles alpha and beta that we've just defined. This angle theta is what we seek to maximize. How do we go about finding theta is the question. Start by taking the tangent of this equation, and we'll see in a minute why that is useful. Tan theta is equal to tan of alpha minus beta. And this, using standard trigonometry, is equal to tan alpha minus tan beta divided by 1 plus tan alpha times tan beta. Now, if we define the bottom of the painting as the point A, the top as the point B, the eyes of the observer as the point H, and the horizontal line through H meeting the wall at the point C. So, from triangle HCB, which is a right angle triangle, we get the value of tan of alpha equal to B minus H divided by X. And similarly, from triangle HCA, we get tan beta equal to A minus H upon X. And now we immediately notice that these values of tan alpha and tan beta go into the previous line, which helps us calculate the value of tan theta, and from there the value of theta. Now the other thing to notice is that as theta increases, the value of tan theta also increases. For all values of theta lying between 0 and 90 degrees. And why is that? Because the derivative with respect to theta of tan theta is equal to sec square theta, which is always positive. Or in other words, tan theta is an increasing function. And so what this really means is that when we are looking to find the maximum value of theta, it really is the same thing as the maximum value of tan theta. We had calculated above that tan theta is equal to tan alpha minus tan beta divided by 1 plus tan alpha times tan beta. Substituting the values of tan alpha and tan beta, we get b minus h upon x minus a minus h upon x divided by 1 plus b minus h upon x times a minus h upon x. Couple of terms cancel in the numerator, and this is equal to b minus a upon x divided by, taking a common denominator in the bottom part of this expression, we get x square plus b minus h times a minus h divided by x square. 1 upon x cancels across the numerator and the denominator. And now multiplying both the numerator and the denominator by x, we get tan theta is equal to x times b minus a divided by x square plus b minus h times a minus h. And this is the expression that we seek to maximize. Now, maximizing tan theta, or this expression, is really the same thing as minimizing the reciprocal of tan theta, which is 1 upon tan theta. And this is equal to x square plus b minus h times a minus h divided by x times b minus a. Now, why did we do this? The simple reason, which will become obvious in a minute, this is a simpler expression to handle when we get into the calculus in a few steps. We'll come back to this point. Meanwhile, notice that b, a, and h are constants. They're fixed numbers. And x is the variable, the distance between the observer and the wall. So, we seek to find the minimum value of 1 upon tan theta as we vary the variable x. And to do this, we simply take the derivative with respect to x of 1 upon tan theta and we set it equal to 0. Using the above expression for 1 upon tan theta, we get 1 upon tan theta is equal to x square divided by x times b minus a plus b minus h times a minus h upon b minus a times x. And we rearrange this slightly to just call out the constant terms separately. We get, in the first term, 1 upon b minus a multiplied by x plus, again, separating out the constant terms, b minus h times a minus h divided by b minus a multiplied by 1 upon x. Now we save ourselves the trouble of writing all of these constant terms again and again. So we denote the constant in the first term by p and the constant in the second term by q. So the whole expression can be written more simply as px plus q upon x. Notice that it is because of this simplicity that we started to work with 1 upon tan theta. And so we have this expression where p is equal to 1 upon b minus a and q is equal to b minus h times a minus h upon b minus a. To find its minimum value, we take the derivative with respect to x of px plus q upon x, and this is equal to p minus q upon x square. And we set this equal to 0 to get x is equal to the square root of q upon p. And to determine whether this is a maximum or a minimum, we take the second derivative of px plus q upon x, which is equal to the derivative of p minus q upon x square, which is equal to plus of 2q upon x cube, which is a positive number. Therefore, one upon tan theta, which is equal to px plus q upon x, is minimum when x is equal to the square root of q upon p. Substituting the value of q and p, we get x is equal to the square root of b minus h times a minus h upon b minus a, divided by the value of p, which is equal to 1 upon b minus a. 1 upon b minus a cancels across the numerator and the denominator, and this optimum value of x is equal to the square root of b minus h times a minus h. And at this value of x, 1 upon tan theta achieves its minimum, which is equal to the value of px plus q upon x when x is equal to the square root of q upon p. This is equal to p times the root of q upon p plus q upon the square root of q upon p. Which is equal to root pq plus root pq, which adds up to 2 times root pq. Substituting the values of p and q, this is equal to 2 times the root of 1 upon b minus a times b minus h times a minus h upon b minus a. This is equal to 2 upon b minus a multiplied by the square root of b minus h multiplied by a minus h. So, tan theta achieves its maximum value equal to b minus a divided by 2 times the square root of b minus h times a minus h. Or in other words, the maximum value of theta is equal to tan inverse b minus a divided by 2 times the square root of b minus h times a minus h. And this value of theta is obtained when x is equal to the square root of b minus h times a minus h. And these are the values for the optimum location of the observer that gives him the best viewing angle of the painting. Let's put in the values of a, b, and h. If a, which is the bottom of the painting, is equal to 8 feet, b, which is the top of the painting, is equal to 20 feet, and let's assume that the height of the observer is equal to 6 feet, then the optimum location of the observer, x, is equal to root of b minus h times a minus h, which is equal to the square root of 20 minus 6, which is 14, times 8 minus 6, which is 2. Therefore, x is equal to root 28, which is equal to 5.3 feet away from the wall. For this value of x, tan theta which is equal to b minus a upon 2 times the square root of b minus h times a minus h is equal to 12 divided by 2 times the square root of 14 times 2, which is equal to 6 upon the root of 28. Therefore, theta is equal to 48.6 degrees. Therefore, the best viewing angle, the maximum value of theta, is equal to 48.6 degrees. And we get this when the observer is located at a distance of 5.3 feet away from the wall on which the painting is hanging. All right, before we close, let's take stock of what we have learned. First things first, please draw the figure. I cannot emphasize that enough. It will make the problem solving so much simpler. Now, this particular problem is disguised as a Sherlock Holmes and Professor Moriarty story. But actually, it is a pretty well-known optimization problem. Once the equation is set up, one has to go through the standard differential calculus steps to find the maximum viewing angle. But this case is a wonderful example of how we can be smart about it. There are at least 3 distinct tricks that are used in this solution to dramatically reduce the amount of work required to find the answer. First, we need to maximize theta. But if we try to do that, the calculation will involve the derivative of the inverse of a trigonometric function. Instead, we notice that tan theta increases monotonically with theta, which implies that theta will achieve its maximum when tan theta achieves its maximum. And it turns out that the derivative of the expression for tan theta is much simpler than if we had to handle just theta. So we choose to work with tan theta instead. Next, we notice that the expression for tan theta is the ratio of 2 polynomials, the smaller power in the numerator and the higher power in the denominator. Now, yes, we can calculate its derivative using the quotient rule, but if you think for a minute, it is much easier to take the derivative of the inverse, meaning minimizing 1 upon tan theta. 1 upon tan theta will have the higher power terms in the numerator and will be divided by a multiple of x in the denominator. Since this is much simpler to handle, we change our goal to minimizing 1 upon tan theta instead of maximizing tan theta. And this saves us a lot of unnecessary labor. Finally, there are a lot of constant terms that are a part of the final expression. The solution combines them into the consolidated constants called P and Q. This reduces the risk of error and saves time because now you don't have to repeatedly write long expressions line after line. So the combination of these 3 steps, looking at tan theta instead of theta, minimizing 1 upon tan theta instead of maximizing tan theta, and combining constants into just 2 summary constants. Doing all of this makes the problem solving a lot more efficient and saves us time. One last point, if you are solving this problem for an exam, the correct answer is that Moriarty should stand 5.3 feet away from the wall for a maximum viewing angle of 48.6 degrees. But in real life, there are constraints, and the maximum or minimum might not be easily attainable. So we frequently ask ourselves the question, how much do we lose if we deviate from the perfect answer? In this case, what if Moriarty could not get to the spot 5.3 feet away? Or if he knew the risk of being spotted if he stood exactly there? Well, to answer that question, I drew a chart of the viewing angle versus the distance from the wall. It confirms our calculations. When x is 5.3 feet away from the wall, Theta is indeed 48.6 degrees, which is what we had calculated. From here, if you come closer to the wall, meaning if you move to the left in this chart, the viewing angle will drop rapidly. So we choose not to do that. However, if we stepped away from the wall, meaning we move rightwards on this chart, the viewing angle drops much more slowly. In fact, if you went from 5.3 feet away to 8.8 feet away, the viewing angle drops only slightly from 48.6 degrees to 45 degrees. That is not much of a compromise. So to summarize our learnings from the case, take 30 seconds first to observe the expressions in front of you. Launching directly into the calculations might not be the best way. Sometimes simpler options are available, and this case is a good collection of what those shortcuts might be. Second, in real life, sometimes compromises are needed. And if we examine the sensitivity of the optimum answer to changes, we could easily make those compromises. In this case, we saw that going closer to the wall led to a sharp drop in the viewing angle. But if you step away, the viewing angle did not drop that much. In real life, it is usually good to know that we have these choices. So that's it. We have it all figured out. Moriarty is cornered, but maybe not. If he too did those sensitivity calculations, you see how the use of the right mathematics, in this case differential calculus and smart shortcuts, allowed us to cut through the fog of the problem and get to a practical and precise answer. That is why mastering mathematics is so important. I hope you had fun, and I will see you back at MathMuni for the next story, where mathematics comes to our rescue and saves the day. Meanwhile, check out mathmuni.com for hundreds of mathematical problems across a range of topics. We are rapidly expanding our collection and would love to hear your feedback. Please drop your suggestions in the comments below. Bye for now.